First of all, I'm very happy to, I'm very happy for being a member here and giving a talk. I would like to thank the faculties here for inviting me, and a lot of friends, in particular Professor Yao, for doing the recommendation for me. Today I'm going to talk about the incompressible elasticity in two space dimensions, and this is a joint work with Tom Sideris, Professor Tom Sideris, and Professor Yi Zhou. Here is a short list of the contents of my talk, and in the first part is the PDE. I will introduce our PDE for the elastic waves, and then we move on to the key questions of this problem in mathematics, and then we talk about its main difficulties, and on the meantime we will introduce some recall some previous progress in this field. And in the last part, we'll talk about the recent result on the almost global variable list of small solutions in two space dimensions. Here let me claim that recently after a lot of after many stimulating discussions with Professor Bogin, I have proved the global variability of this problem, but he's so generous, and he insists a lot being on the alternate. Okay, let me begin. Let's begin with the flow map, the concept of flow map. Suppose we have suppose we have a point, a material point at the initial time t equals to 0. In a domain omega, and at time t, the point is moved to another position, called x. Of course, x is a function of t and y. The domain becomes to omega t. Here we are interested in diffeomorphisms, so we assume that the flow map X is smooth, and it has a smooth inverse. We use the terminology that we will call the of course here unknowns can be expressed in both in the functions of ty and the functions of tx. So we will call those the ty to be Lagrangian coordinate, or call tx to be Euler coordinate. Okay. The flow map X can generate a velocity field at time t and the spatial position x. The velocity field is defined to be the time derivative of the flow map, the displacement. It's very simple. Alternatively, you can also think of that for a given velocity field, it can generate a flow map by solving the following ODE. Here, the y can be you just look on y as a parameter. Okay, for perfect fluids, the dynamics is determined by the following Lagrangian. Of course, this is related to the kinetic energy. It's very simple. It is known that the first variation of this Lagrangian function and the constraints of incompressibility gives the well-known Euler equations. But for elastic materials, the motion is not only determined by its kinetic energy, but also determined by its elastic energies. So the elastic energies will be related to the concept of deformation gradient tensor. So the deformation gradient tensor is defined to be the Jacobi matrix from the Lagrangian to Euler translation. So what do we mean by incomparability? By incomparability, we mean that the volume is preserving along during the dynamics, during evolution. So early domain here, it moves in time. The volume of the domain is invariant in time. So in mathematics, this is equivalent to this identity, determined f equals to 1, because the volume preserving just means this identity, right? For early domain here. Okay. So we consider the the most simple, the most basic story energy function. In this case, W is just a function of the deformation tensor. So for isotropic materials, we can show that the W depends on F only in terms of the invariance of F transpose F. Of course, this is another matrix. In two space dimensions, the invariance of this matrix are just the trace and determinant. Because in two space dimensions, we only have two invariants. One special case is that W only depends on the determinant part of this matrix. So this is the perfect fluids. Especially in the incompressible case, we know that determinant is 1. So W is just a constant. So in the perfect fluids, you do variation, you just go to the Euler equation. There is low potential energy. Another case is that is a hooking elastic case. In this case, W is just is the trace of this matrix. Okay, this is for the incompressible case. In fact we can show that any incompressible elastic energy is just a small perturbation of the hooking elastic case. So this is the most typical case and the most essential case. So below we will just focus on this hooking elastic case. And in this case, we are in the hooking case. So the Lagrangian function just takes over the form. This is kinetic energy, and this is potential stored elastic energy. And here we also have a function P. So P is the Lagrangian multiplier because we are focused in the case of incompressibility case. So the determinant is always 1. You can prove that you can show that the incompressibility condition determinant equals 1 is equivalent to divergence of V equals to 0. It's very simple. You can show this by the conservation of mass. Okay. Then we can get the Euler Lagrangian equation of this Lagrangian function. It's very simple. This is D'Alembert of X. This is wave operator. And then here you have this part is due to the Lagrangian multiplier. It's just equal to 0. You will see that this is the quadilinear wave equations. Of course, here due to the existence of pressure, so the system is non-local. And this is the incompressible constraints. Of course, this is nonlinear too.
What is this F?
F is the deformation gradient here.
Yes.
It's a matrix.
And then you have a minus the thing.
Sorry. This is inverse transpose.
Oh, it is
Inverse transpose. Okay. Now, what's the key question? Our key question is to solve the flow map. It's very simple. To solve the for PD, we hope to solve the about PD. So we are formulating the equation in Euler coordinate. We will see that it is quadilinear wave type equations. So in general, in those cases, the interest are centered around the small data global regulated case. Okay, before moving on, let us take a look at the invariant groups of the system. Suppose xp is a critical point of the Lagrangian function. You can define x tilde. Here q is defined to be e to the sa. Here a is a constant matrix. It's antisymmetric. So you can check that the qs is standard orthogonal matrix. Very easy. Then you can define x tilde. This is a kind of rotating for the original flow map. Then you can check that x tilde p tilde is also a critical point of the Lagrangian function. So you can easily derive from this invariance group that the equation is invariant and the rotating invariance. That means that if you apply the rotating operator to the equation, the operator commutes with the equation. So similarly, you can also check that the skinny is also commute. Skinny operator is also commute with the system. And here, a skinny is defined to be if the skinny operator is applied to the vector field, and then this, you have a correction. You need a little bit correction. If it is applied to a scalar function, then it is just skinny. So omega is also the same thing. If omega is applied to a vector on vector field, then it is the first part is the angular derivative part, and the second part is a correction. If it is applied to a scalar, then just the angular derivative. But unfortunately, there is no Lorentz invariance for the system. Okay, here is the system in Euler coordinate. You can see that the left-hand side part of the momentum equation, this part is exactly the Euler equations. And this part comes from the elastic force. And for this equation is just, this equation just describes the, describes that the material space-time material derivatives commute with each other. Of course, this is absolutely true for smooth solutions. So the third one is just incompressibility. So this is a very basic equation. And here you can, if you remember this equation, here F, the equation for F has exactly the same form for the vorticity equation or Euler equations. So green VF is matrix. Here it means this green V is IJ's component equals to green V IK F KJ. Here green V IK means partial VI or partial XK. Okay. So this is exactly the form for the vorticity equation or Euler equations. But here F is a matrix, not a scalar. And here the momentum equation contains Euler as a Euler equation as a subsystem. But here we are interested in solutions which are small, in the sense that the solutions are close to their equilibrium. The velocity, the equilibrium of velocity will be 0, and the equilibrium of the deformation tensor will be identity. So this will give us some dispersive effect for this equation. Okay. Before moving on, let me talk a little bit on the connections of this equation to other fundamental systems in fluid mechanics. So if you add a Laplacian term in this equation, you got a so-called viscoelasticity. And if you ignore the elastic force in this equation, you got Euler equation or Lewis-Dulce equations. And thirdly, if we will prove this guy. It's divergence. Each column vector of the F is 0. It's also divergence free, not 0. Each column of the matrix of F is divergence free. So you can always assume that F has this form. Here we are in 2-dimensional. So green probe is just the gradient operated perpendicular to the original gradient. So phi is a vector. Okay. So you can rewrite the equation in terms of phi, and you find that, of course, here phi is a vector. If you remember for the magnitude dynamics, and if phi is a scalar, then this is exactly the magnitude dynamics. So the equation is very related to MHD too. So you can just think the elasticity system is a vector version of the magnitude dynamics. Okay. Now let us take a look at the main difficulties of this problem. And first, we linearize the equation around its equilibrium, and you differentiate both equations with respect to time, and you see that the linearized equation for V is just D'Alembert of V equals to 0. And for G, you see that D'Alembert of G equals to curl of G. So if this guy can be treated as a forcing term, then the main part will be a wave equation. Unfortunately, this is indeed the truth, because we find that the curl of G is a quadratic form of G and gradient G. So basically, this is not a linear term, and this is a physical identity. It's always true. This was first found in my thesis. Okay, then since it is a wave type equation, it's with quasi-linear nonlinearities. So the key point here for long-time existence is the first one is dimension, because for wave equation, for wave equation the we are interested in the non-time behavioral solutions. So we need the time decay rate of the solutions, of the linearized solutions. So the first guy will be dimension, because for wave equation, linearized wave equation, the solution decays like t to the minus n minus 1/2. So if the dimension is large, then the decay rate is very fast. So that's better. If the dimension is low, then the decay rate is very slow. So that's worse. So now we are in dimension 2, so it's not a good case. The second one would be the structural nonlinearities. In general, if we need a law structure for the nonlinearities, which will give us the line relevance along the line cone. If there is no law structure, in general, the solution will blow up in finite time. We will see this a little bit later. Okay, the heuristic is just here. It's very simple. Let me write this down. This is all the. I will only talk about the ideas, and I will ignore all the technical part. So here is V or gamma alpha G L2 long. Okay. Or something. Or whatever. Okay, dx. So by energy estimate, of course, here gamma, I will explain gamma, what's gamma later. You can do energy estimates for this equation, and you can get this kind of estimates here. Anyway, you can take one of them out by L infinity norm. The ES is just defined to be L2 norm or V or G. Okay. Here we have quadratic nonlinearity for this equation. We hope to get a global control for the energy ES, right? So of course we hope to get a decay type estimate for the L infinity norm or ds d some power or d a lot of derivatives of V in L infinity norm. So this is a decay type estimate. Of course we hope to do this in terms of the energy, so that we can have a closed argument. So we are in three cases. The first case is if alpha is very large. For instance, if alpha is bigger than 1, then we are in a subcritical case, because if alpha equals to 1, and just insert this guy here, then you can prove that if the initial energy is small, then the energy will be keeping small for all the time, and then coming back you get this decay rate. Then you close the argument. This is a very easy case. But if alpha equals to 1, then you are at a critical case. In this case, in general, you can only get almost global existence. But if you want to have global existence, you need extra works. But if alpha is less than 1, then you are at a supercritical case. And this is, of course, this argument is not enough. You need much extra works. So, I'm sorry.
Treat all those cases.
No. And those are in general case. For LA nonlinear wave equations, you can always do this kind of things. But now we are in the two-dimensional case, so this guy would be a half. I will talk about this later.
So you are supercritical.
Yeah. Okay. Kleneman, Professor Kleneman introduced the so-called vector field theory, which provides a uniform method for studying nonlinear wave equations. His method basically says that if you define S to be a scaling operator, and omega to be the rotation operator, and L to be the Lorentz operator, then you can prove this inequality. For wave equations, you can prove that this is bounded by initial data. So for solution of wave equations, you can prove that of course you need a derivative. Here you also need a derivative, and for solution of wave equations. Then you see that the solution will decay like 1 over half n, t to the minus half n minus 1. This is the decay rate.
So the gammas are what? One of those differential operators?
Gamma is not only those kind of operators, but also include space-time. So gamma is gamma is derivative with respect to space and time, and this rotation, scaling, and Lorentz. Okay. All of them. And then you can see that if the space dimension is bigger than is no smaller than 4, then you have a very good degenerate. And then the above heuristics can get through very easily, right? But this is not easy before the vector field theory. So for n is no smaller than 4, then it is subcritical case. Global output is easy consequence of vector field theory. But if n is 3, then we are at a critical case. In this case, we need an extra constraint assumptions on the nonlinearities. That is the so-called law condition. And this is a landmark work in this field. It is obtained independent by Clenham and Christodoulou. In 2 space dimensions, this is a supercritical case. It's not easy. So in this case, the result was obtained 15 years later by the Professor Alinak. And okay.
What did he do?
He proved that in 2 space dimensions, for scalar wave equation, if the nonlinearity satisfies the law condition, then the system is globally well posed for small elite data. Okay. This paper was published on Invention of Math. But for all of the above results are for scalar wave equations. That means you need the Lorentz invariance of the system. But for elasticity, it's much more involved because elasticity you have 2 families of waves. One is pressure waves, the other is shear waves. So those 2 families of waves propagate with different speeds. So it's so you don't have Lorentz invariance anymore. I'm sorry.
Are you still in the incompressible case or no?
I'm doing the incompressible case. I'm doing the incompressible case, yeah.
But then there's only one speed, I thought.
Let me talk a little bit later. You cannot see that because you still have 2 different families of waves, but one of them degenerate. The speed is infinity.
Okay, yeah.
Okay. Now those are basically history. So I'm talking about the previous progress. So here I didn't mention they are compressible, incompressible. Okay, next page will be that. So here another difficulty is that people don't know how to use law condition in this case because the law condition is not as easy as for the model case for model wave equation case. So anyway, but in 3 dimensions, the heuristic is that the problem is critical. So those has been done by Tom Series and Argimi in the 3-dimensional compressible case. All of those papers are published in Arlos or Invention. So in the incompressible case was also solved by Tom Series and Somerses later on by a series of papers. This is a 3-dimensional case. This is compressible, this is incompressible. Okay.
But these are all critical, or?
The 3D is critical because the time degenerate for the linearized equation is 1 over t. Okay. So what's the open question now? The problem remaining is the first is in 2D is wave systems with different propagation speeds, and this problem is almost untouched because we even don't have non-trivial non-time existence theory for this problem. The second one would be the compressible elasticity in 2D. This guy will, in general, people think this is more difficult than this because the linearized equation here is more complicated than wave system case. The linearized equation here is a hyperbolic system. It's not a Canine Dynamo-Borsian operator. And third case is incompressible elasticity in 2-dimensional case. Because in this case, you even have a local effect. Of course, in this case, one of the pressure wave degenerate. So you only have 1 propagation speeds, but you deal with the non-local effect. But in all of those cases, there's low Lorentz invariance. Okay. So our result is that in 2-dimensional case, the last question, in 2-dimensional case, incompressible case, if the Elite data is sufficiently small, then the solution is almost global well posed. By almost global, it means that if the Elite data is of epsilon order, then the lifespan of the solution is exponential to 1 over epsilon. That's the result. Okay, let me mention a little bit on the result on the viscoelasticity. If you have a Laplacian term in the equation, in the momentum equation, just in the momentum equation, then this is the so-called viscoelasticity. In this case, the two-dimensional case was solved by these three, Fang Hua Ning, Chun Liu, and Ping Zhang. And also, Yi Zhou and myself used a different method for this problem. And the three-dimensional case is due to Liu, Zhou, and myself. And we also studied some large solutions in terms of the small string solutions. Okay. If you are interested in more details, you can take a survey, take a look at the survey paper by Ning. Let me mention that in this case, when you have a Laplacian, the 3D case is difficult and 2D case is easier. But if there is low Laplacian, the 2D case is more difficult than 3-dimensional case. Okay. Okay.
Can you go back to the statement of the theorem?
Uh-huh.
So beyond this time, you expect problems to appear or not?
I just claim that we have proved this global well posed list.
Oh, you have?
Yeah, but it's too tight for me to talk about that this time. I need to do some preparations. My English is not very good.
So you have global existence?
Yes, just, of course, after many stimulating discussions with with him. Yeah. Okay. Okay.
But the answer is there's nothing. It's supposed to be fine after that time scale.
Yeah, I think so, but you know, I need more careful. Yeah. Okay. Now let's take a look what's the difficulties here. The first one is dimension 2, right? The time degenerate is supercritical. This is the first difficulties. The second one is the structural nonlinearities. So in the incomparable case, you cannot impose extra assumptions, especially in this hooking case. So what's law conditions? You need to find out. You can for wave equations you can add extra assumptions to force the nonlinearity satisfies law condition. But for this is a physical case, you cannot add any extra constraints anymore. So you need to find it out. The third one is that this is incomparable case, so you have a nonlocal effect when you deal with this this guy. Okay, let's begin the proof. I will just present the main ideas of how to prove this problem. There's low technical part. So first, due to the invariance, you can just apply those gamma. In our case, there is no Lorentz anymore. No Lorentz. Okay. It's just scaling, rotation, and translation invariance. Okay. So you can apply those gammas to the equations, and those gammas commute with the equations. So you got a very good form, and also divergence of gamma alpha v equals to 0. Okay. And here, what is the rotation operator here? Because we have matrix, right? Those are similar as before. But if alpha is applied to a matrix, then the first part will be the angular derivative part, and the other part is this is the standard knee bracket. And A, if you remember, A is an antisymmetric constant matrix, so it's just a modification. We will often use this decomposition. The green operator along the radial symmetric direction and the angular direction. Of course, we have a lot of constraints. The first one is that each column vector of G is divergence free. So those operators can also commute with this guy. And the curl operator, the curl of G is a quadratic form. So you also have this nice constraints. Of course, as a lot of people did in this field, people always use vector field theory. So we also need Clemens vector field theory. We define the energy to be the gamma alpha derivative of the unknowns. I have two norm of this guy.
When you say alpha is less than k, you're considering higher powers of these operators, I guess.
I'm sorry?
No.
Okay, we only care the biggest guy. Oh, we also need the weighted energy norm. This weighted energy norm was first introduced by Kleinem and Series in their paper a long time ago. We are going to prove the energy estimate can be closed if the lifespan is no bigger than the e to the 1 minus epsilon. So what we are going to do is this not only is, of course you have L2 norm square. Okay. You have some okay, it's 1, 2, 3, so you have cubic, right? But what we are going to do is we hope to get an extra decay rate. So we have to get this extra decay rate. How to get this? First, because we are in the wave equation case. Let's say this is r equals to t. So we divided the space-time into two parts. The first part is here. Let's just call omega 1. The other part is omega 2. Okay. Okay, this is also omega 1. And this part is omega 2. And we call this is the ladder cone. It's ladder cone of the this is the characteristics. So we first consider this part. These regimes are away from the ladder cone. So here, the decay rate of the solution in omega 1 in this regime will essentially be obtained by this weighted operator, those weighted energy. So in this case, when you do energy estimate, one of this guy could have a weight T minus R. So this is why you got the extra decay rate here. So below we are focused on the case this part. Of course, this part is not easy because we have the local operator. In this case, T minus R doesn't commute with the zero order Ritz operator, so you need some extra work. Anyway, but this part can be done. So the main difficulty are here along the characteristics. Okay. So below we were focused on this case to get this time decay. We need to use the nonlinearities of the structures of the nonlinearities. The first structure is due to the incompressibility. Divergence v equals to 0, and each column of f is divergence free. So what you have from here is that this combination and this combination is a good unknown. Here, omega is just defined to be x over r. Okay, by good unknown, we mean that this guy decays much faster than the linear velocity equation. If you can check the paper, you will see that these two unknowns are even much better than the linear velocity equations. This is just because the incompressibility. It's not due to the wave nature of the system. Okay. We will give a lemma later, a little bit later. The second structure is that we have this identity. This means that the curl of each row vector of G is a quadratic form. So this identity gives us that the G omega perp is a good unknown. But this will be as good as the linearized case. But of course, you also do linearization. So you will see that this guy will decay like 1 over t. The third one is we call this an intrinsic good unknowns. This good unknown can be seen by the Arlinak's ghost weight method. And of course, this is the first time that we apply Arlinak's ghost weight method to the nonlocal problems. Okay. Then in this regime, since we need to use Arlinak's ghost weight, that means when we do energy estimate, we have a weight here. We have some weight. So the pressure term cannot be killed just using divergence free, because we have a weight. If there's the weight, then we just use divergence free, and the pressure term disappears. But here, no. So you need to treat the pressure term as a forcing term. So you have to prove that the pressure is also satisfies the kind of law condition. Okay, this is the first time that this is the first time that we prove that the pressure for incompressible flows satisfies the law condition. Of course, this one is easy. What is F here? F is just the nonlinearities in the momentum equation. So this is known by theorists did this before in their paper, but this one's new. Using this formula, we can use the law structure of the pressure term. And then we translate those heuristics into mathematics. The first one is we define LK to be the linear part of unknowns, and NK to be the nonlinear part of unknowns. Of course, notice that here we have a weight here, T. So if we can estimate this nonlinear form, we will gain a decay factor. Okay. So then what do we have? We have first, since W is a good unknown, then what we have is this guy is bounded by the linear part. What does this mean? This means that in this regime, near the nut cone, R is almost T. So this guy decays like in L2 long. In L2 long, this guy decays like 1 over T. This is very good. In L infinity long, this guy decays like 1 over square root T. So this guy decays like 1 over T to the minus 3/2. Of course, this is absolutely much better than the solution of the linearized solution of the two-dimensional wave equation. Okay, for two-dimensional wave equation, the best decay rate is 1 over square root T. If you use law condition, the best you can get is 1 over T. But here, what we have is 1 over T to the 3/2.
Why? You're getting that because you're using the good coordinates?
No, we are using the structure. The flow is incompressible. The flow is incompressible.
Yeah, but you have to, the right observables have to be used, right, in order to get this decay, or not.
I'm sorry.
In other words, is the use of these omegas or what you're using, I'm trying to understand why, since the usual wave equation you get, square root 1 over square root time, what is it about what you're doing that gives you faster decay? You said incompressibility, but
Incompressibility, yes. Because an explanation for this, you can say this here, is for incompressible case is divergence of V equals to 0, right? Then what you have, you can decompose this operator because we are here, so we don't care it's 1 over R character. So what you can decompose the gradient operator to be radial part, okay, and the angular part, right? But this part decays very good because this is nothing but omega V. And here you gain this is just T, right? This is what you gain. So this equals 0. So this because the structure of this system it has nothing to do with wave nature of the system. It's because incompressibility. Okay. And the second guy is the same thing. But the third guy is also good because on the right hand side you do need the nonlinear term. So in this case you have a little bit less decay, but you still have as good as linear case. But these two cases are better than linear case. Okay. So for this quantity now you can see that in L2 long, this guy decays like 1 over T. But but if you do L infinity long, this guy decays like 1 over T minus 3/2. Okay. Of course, you have a price. The price that you need a spatial derivative. You need a spatial. If you remember in our equations on the right hand side. Okay, just sorry. in the equations, you only have one spatial derivative. So but you always have one. You always have one. You only have one space derivative. So if you want to have most time decay rate, then you have to waste a spatial derivative. Of course, you cannot always do this, because if you want the most decay rate, then you have to take L infinity norm. Then you lose regularity. So sometimes we still need to save this derivative. Then we do this estimate. So there is no spatial derivatives. But then you only have L infinity estimate. But still, what you gain is what we have is the time decay. What you have is 1 over t. Okay. Let me just give the proof. And next will be this compilation. This compilation. If the sign is plus, then you got a factor which is t plus r. But if this is minus, then you have a factor t minus r. Okay. The right-hand side, one part is linear, the other part is nonlinear. And this part, the estimate for this part cannot be, it's good but not so good. So in this case, this estimate is as good as a linear case. You can just think it as that. Let us take a look at the proof, because it's very simple. First, you use the skinny operator to rewrite the equation, okay, reformulate the equation. You just multiply both equations with respect to t, multiply both equations with t, and then you reorganize them, and you can get these two equations. Then you plus them together and minus them together. You can see that the combinations, you can see what we want is there. And then you just estimate the right-hand side. That's not too difficult. Okay. And now, if all of the above is settled down, then we can estimate the nonlinearities. Remember that we have a t factor in the definition of the nk. Nk is basically nonlinearities with a factor t. Okay. So of course it is quadratic. So the right-hand side is also quadratic. But what you gain is a factor here. There is a t, right? The proof here, of course, in L2 norm, you need to divide the space-time into two regimes. One is here and the other here. And in the place of omega 1, you need to use the weighted L2 norm, and here you need the good structures of the system. Let me mention that we didn't take the full advantage of the last good unknown yet. That good unknown comes from Arnold's goes-with method. Till now we didn't use that. Now we can estimate the weighted ghost energy, weighted generalized energy in terms of the generalized energy. Okay. Remember that what is the definition of this guy? One part is just the general, one part is just this energy, right? The other part is the derivative of unknowns with a weight t minus r. And here first you can prove that the main contribution of the xk square is just this guy and the divergence of g, not the full gradient. This is the first observation, because the curl of g is a quadratic nonlinear term. Okay. And then you can decompose the gradient v into this and divergence of g into this. We know that this combination can cure with t plus r, and this combination can cure with t minus r. So anyway, you can prove this theorem. And then now we can estimate the last good unknown. The last good unknown, the estimate for the last good unknown is due to the wave nature of the system. Okay. Again, in L infinity norm, you can have a factor r here. Of course, we only need this estimate when r is close to t in this regime. But for the first guy, we only have L2 type estimate. That means in L2 norm, you have the decay rate of 1 over t, but you don't have L infinity norm. So you don't have, what you don't have is, you cannot take L infinity norm to get t to the minus half, 3/2 time decay. So now you only have L2 type estimate against a factor t. Okay. And now we are ready to derive. If you all of the above, you can prove all of the above, then you can derive this energy type estimate. This is the backbone of the whole proof. It's Clemens vector field theory. You can basically in those places you use weighted norms, and here you take advantage of the law condition. You can finish. You can get this energy estimate. Then if you assume that the latent data is sufficiently small, then you can get that the lifespan of the solution will be exponential to 1 over epsilon. In this time regime, the energy will keep small. This is the so-called almost global variable list. Okay, this is the final result. I think I just stop here. Thank you very much. Learn Chinese.